Hello friends, so today we are going to solve 4 questions, and these 4 questions are from electrostatics. Okay. So the first question, 1 second. We are given a sphere of radius r has a charge q distributed uniformly over its surface. How large a sphere contains 90% of the energy stored in the electrostatic field of this charge distribution. So we have to find out basically the size such that it contains the 90% of the energy. Okay, and that energy will be stored in the form of a electrostatic field. So we are given a spherical shell, okay, and its radius is given to us as r. So we are given a spherical shell and its radius is given as r, and the charge that is distributed over the surface is given as q. Okay. And so first of all, let's find out, try to find out, or rather we can discuss where the energy will be stored. And we know that for a shell, or we can say, or inside a shell, for any point that is at a distance of small r which is less than capital R. Okay. And at this point, you can easily see that the value of electric field will be equal to 0. And if the value of electric field is equal to 0, therefore from here we can say that no energy will be stored. Okay, so we can say the energy stored will be equal to 0 inside the shell. And outside the shell, for any point which is at a distance r and greater than the radius of the sphere, the shell, and in that case the electric field, that is E of r, it is given as 1 upon 4 pi epsilon naught q upon r square. Okay. So it means all the electrostatic energy will be lying outside the shell. From here we can just draw this conclusion. And based on the basic formula for our energy density, we can write the equation. So we can say that our energy density and let us suppose that is given as by small u, then this small u will be equal to over half epsilon naught and E square, and this E will be equal to over E at a distance of r, which we already know. Therefore we substitute it, we get the energy density u will be equal to 1 by 2 epsilon naught, and this comes as 1 upon 4 pi epsilon naught q r square and whole square. Okay. and this will be coming as 1 upon 32, and q square pi square epsilon naught and r raised to power 4. Okay. And so in this case we just found out that if this is our shell and its radius is capital R, okay, and we take a surface which is surrounding this shell and it is at a distance of small r. Okay. It means, and we also found out that the energy inside the shell, or we can say our electric field inside the shell, is equal to 0, and outside the shell in this shaded area, okay, we found out this electric field is our E of R. Okay, based on this we found out our energy. It means the entire energy will be lying only between this ring basically, and that ring is between R and small r. So we can from here write it as energy between capital R and small r. Energy between capital R and small r. And we can just denote it by writing it as capital U from capital R to small r, and that will be equal to over from integration capital R to small r, this our small u, and it comes as our 4 pi r square and dr. And if we want to do it, we can just assume that there is a small surface about this inside it, and by the help of this we are going to get the same equation. Okay, otherwise you can just write it directly also, and we substitute value of u, so we get that our energy from r to small r will be, this will be coming as our, we have 1 upon 32 and that is by 4, and it will be coming as q square 8 pi epsilon naught, and this will be coming as our 1 upon r minus 1 upon small r. Okay, so this will be the energy. So it means the total energy this is small r. Okay. And so you can see that our total energy let us call this a U total will be equal to our q square 8 pi epsilon naught times r. And we have to remember, because it is asking the question, we have to find out the larger sphere such that it contains the 90% of the electrostatic energy. Okay, so for that we assume that the sphere which is going to contain that energy is having a radius of small r. Now we are going to find out the ratio, because we are interested in that the ratio should be equal to the 90%. Okay. So we can say that our energy between R and capital R and our total energy, and that ratio will be equal to our 1 minus r upon small r, and this ratio is nothing but our 90%. Therefore, from here we can easily say that our r upon small r will be equal to 0.1, which gives us that the small r will be equal to 10 times capital R. So this is the larger sphere which will be able to contain the 90% of the energy associated with the small r. Next question. It states that concentric spherical shells of radius a and b such that a is less than b carry charge q and minus q respectively, each charge uniformly distributed. Find the energy stored in the electric field of this system. So we are given spherical shells, and this is the center. Inner one is having a radius a and outer one is having the radius of b. Okay. And inner one is given a charge of plus q and outer one is having a charge of minus q. So we have to find out the energy stored in this entire system. Okay. So we are given the concentric shells. Okay. So we have our inner shell, and this inner shell is with the radius small a and charge plus q. Okay. And then we have an outer shell, and this outer shell is having a radius of b and charge is given as minus q, and it is given that a is less than b. Okay, that is already mentioned in the question, and charge is also uniformly distributed. Okay. So therefore we can divide this entire system into three regions. Okay. So we can say this is our region number 1, region number 2, as well as region number 3. And we know that the energy density will be stored in the form of our electrostatic energy. Therefore, let's find out what will be our electric field in all these three regions. So we can say we are going to start with region 1. So we have region 1, and according to our Gauss law, region 1 is any region which is less than a, and for that the charge enclosed is equal to 0. So we can say that our enclosed charge is equal to 0, and if enclosed charge is equal to 0, therefore by Gauss law we can easily see that the value of electric field is equal to 0. Then we come to our region 2, and okay, so region 1 was our r less than a, and for region 2 this r is greater than a but less than b, and in this case the charge enclosed will be equal to our plus q. You can say charge enclosed will be equal to our plus q. Therefore we can write that our value of electric field at a distance r will be equal to 1 upon 4 pi epsilon naught, and this comes as q upon r square. Now we come to region 3. and region 3 is when R is greater than B. And once again, charge enclosed. And that will be equal to over plus Q and minus Q, which will be equal to 0. So it means, once again, the value of electric field will be equal to 0. And we know that the value of energy density, that is our standard formula, so we can straightforward write that our energy density that is small u is our half epsilon naught and square of the electric field. Okay. And the electric field is only in our region 2. Okay. So we substitute value of E. So we get that our energy half epsilon naught, and this comes as 1 upon 4 pi epsilon naught Q upon R square whole square. So this will be equal to over Q square 32 and pi square epsilon naught and R4. So it means total energy stored which is suppose our capital U, and that will be equal to over U small u and with respect to the volume. So we simply substitute them, we get this as capital U will be equal to, and this is between A and B, okay, and U is our square 32 pi square epsilon naught R4, and our dV will be our basically 4 by 3 pi r cube. We can just derivate it, and we are going to get this as our 4 pi r square and times our dr. And so this pi goes by square and this goes by 8. So we get that U is equal to our Q square 8 pi, and this also goes away square and this goes by 2, and we have 8 epsilon naught from A to B r raised to power minus 2 and dr, and this is quite simple. So we get this as our Q square upon 8 pi epsilon naught, and we have this 1 upon A minus 1 upon B. Okay, so this is the total energy stored inside the shell. Next question. It states that consider a solid cylinder of radius A and a uniform volume charge density as rho. Based on this, we are having 3 subparts to it. Using the energy associated with the electric field, attempt to calculate the total energy per unit length stored in the electric field, including the field inside the cylinder. Part B, calculate the energy relative to the reference configuration where all charge is initially distributed uniformly over a hollow cylinder of large radius capital R. Explain why the field outside a radius of R can be ignored in this calculation. Part C, derive the energy per unit length for bringing the charge from the hollow cylindrical configuration to the solid cylinder configuration. Express your result in terms of the total charge per unit length lambda in the final solid cylinder. So in this case, only the questions are a little bit lengthy. Otherwise, the solution is quite straightforward, except for little bit part of that is tricky here. Okay, we will discuss that as we solve it. So we are given that we have an infinite solid cylinder. Infinite solid cylinder and whose radius is given as small a, and charge density is given to as rho. Charge density is given as rho, and therefore we can write our total charge per unit length. From here we can find out the charge per unit length. Charge per unit length, that is of lambda, will be equal to over rho pi a square. And we are going to use or we can say we are supposed to find out the energy per unit length, and for that we are going to use field energy formula. So we are supposed to find out energy per unit length. Energy per unit length. So that is our capital U will be equal to 1 upon epsilon naught integration E square, and this is our dr. And because the cylinder is given to infinite, so it is much better to calculate the energy per unit length. And first of all, let's find out what will be the electric field. Okay. So we can say our electric field and our electric field we are going to solve for first of all the inside the cylinder. Inside the cylinder, and for inside the cylinder we have suppose any radius r which is less than a, because cylinder is given as having a radius a, and we can easily our Gauss law. So we charge upon epsilon naught, so this gives us our rho r upon 2 epsilon naught. Now outside the cylinder, and outside cylinder r is greater than a, so we get that electric field in this case will be equal to our lambda upon 2 pi epsilon naught times r. Okay, so this is standard formula for our electric field inside the cylinder as well as the outside the cylinder. Okay. And obviously we are going to, in order to find out the total you can say electric field, we are going to use this particular relationship. Okay. And it means we are going to integrate the integral from a to minus infinity. And for this particular case, okay, because this r is in the denominator, and so let us sort it out first of all. So let us call this as equation 1, and we are only going to consider it on this part, integral part, okay, because that is going to create a problem. So you can say from equation 1 we are going to do integral of our electric field, okay, with respect to our dr, and our this limit is going to vary from our a to infinity, okay, for r greater than a. And in this case, if you substitute, we are going to get our electric field will be equal to this comes as from a to infinity, and this will be basically dr upon r. Okay. And the integral will be equal to natural log of r. Okay. And natural log of r, it means we are going to substitute one of the value of r as infinity. Okay. And that creates a problem. Okay. So which means this particular our equation, it diverges logarithmically. Okay. You can say it diverges logarithmically, or we can say we are going to have a infinite energy. Infinite energy. And we know that is not physically possible. Okay. That's why we always compute our energy relative to a reference configuration. Okay. Because in the question, if you look closely, it states that in the first case we have to simply calculate the energy, which we calculated, but we found out that it tends to be infinity. Then in the second part, we are going to calculate the energy with respect to a reference configuration, and it means with respect to a cylinder whose radius is r, larger r. Okay. So this is the meaning of this. So part A is a little bit of problematic because of this infinite energy, okay, because we know this is physically not possible. Okay. Therefore, from here we can say that compute energy relative to a reference configuration. And reference configuration is given itself in the part B. So we are going to stick with that. So this reference configuration, it is given that we consider a thin hollow cylinder of radius r. So this reference configuration is thin hollow cylinder and whose radius is given to us as capital R. But the value of the electric field will be same for both the cases, okay, because here also this R is greater than A, okay, and in this case we can simply write that the field for R greater than capital R is the same in both cases. In both cases. Okay. So it means from here we can draw an important conclusion. Therefore, we can say we ignore the region when small r is greater than capital R. So this was one of the key aspect of our this. So it means we are only going to integrate because the limits are important in this case. Okay. Therefore, we can say we integrate for first is when our point lies between 0 and A, and the second when our the radius basically, not the point, it lies between A and capital R. Okay. And the first case, we know in this case the field is inside the solid cylinder. Field is inside solid cylinder, and in this case difference in the fields. and we can just draw the figure also. Okay, so let's draw a, first of all, the solid cylinder. So this is a solid cylinder. Suppose this is the axis and we are given a radius of a, and like for reference we are going to consider a larger cylinder whose radius is capital R. So this is the radius of our reference cylinder. So it means, and like I said, that for R is greater than capital R. Okay, so it means any point which is lying somewhere here. Okay, so in this case, this point is our at a distance R from our. So this is at a distance R, but it is greater than capital R. Okay, so it means the situation comes back to the same, okay, which we from here. Okay. So therefore, we are simply going to ignore this part. So we will be only interested in finding out the electric field in the two regions. One is between 0 and A, which is basically a solid cylinder, and then we are going to solve it from A to capital R. Okay, so this is the basic meaning of this entire question. Okay. And therefore energy inside the cylinder, and we are supposed to find out the per unit length. So we can say our energy inside the cylinder, it means when R is less than A. And we are going to discuss the energy per unit length. Energy per unit length, and that is our, let us call this energy as U inside the cylinder, and per unit length will be equal to 1 upon epsilon naught integral, and this is our E square, and we get this as our 2 pi R dr, and the limits will be from 0 to A. And we substitute value of E, electric field, that is our rho R upon 2 epsilon naught. So we get this as our 1 upon 2 epsilon naught, and this is our 0 to A, and we get this as our E square. So E square will be our rho square R square upon 4 epsilon naught square multiplied by 2 pi R times dr, and this 2 goes by 4, and rest will be same. So we get inside, we are going to get this as R cube. So R cube will be giving us R4. So we can say, and this 2 and 2 will be equal to 1 by 4. So that will be equal to over 1 by 16. Okay. And we have this as rho square and pi upper limit only a raised to power 4 divided by epsilon naught. Okay, this and sorry, this is a square, this square cancelled by this epsilon naught. So we are left with only epsilon naught. So this is our, and we know this is our U inside the cylinder, energy inside the cylinder per unit length. But we also know that our lambda is equal to rho pi a square. So we can simply substitute it. We get this as our energy inside the cylinder per unit length will be equal to lambda square, and this will equal to 16 pi okay, we substitute it entirely. So this we get our lambda square will be equal to rho square, pi square and a square. Okay, so we need a pi in the denominator, and this will be our epsilon naught. Okay. So this is our energy per unit length inside the cylinder. Now we come to our second part, that's energy between when R lies between A and capital R. So you can say our energy between whenever A is greater than, sorry, I've written reverse. So we have our R which is greater than A but less than capital R. Okay. So it means, and so we can write this as our energy, that is our U, and that is, let us call this as between, per unit length will be equal to same formula, 1/2 epsilon naught integration, and integration is from A to capital R, and we already know all the equations, so this comes as a lambda upon 2 pi epsilon naught R whole square, and this comes as a 2 pi R times dr. Okay, so basic formula we already know it. Okay, where it went, yeah. So this is our basic formula for our electric field outside the cylinder, and this was for inside the cylinder. So for inside we use this relationship, and for the outside we used this relationship. Okay. And the basic formula of electric field is this one. Okay. So we simply substitute our value of our electric field as per our requirement, whether it is inside or whether it is our outside. So now it is quite simple. Okay. So we are going to get this as our electric field energy between per unit length will be equal to, and this will be our lambda square 4 pi epsilon naught natural log of capital R divided by small a. It means total energy will be equal to the summation of the both. So you can say total relative energy per unit length. Total relative energy per unit length. Let us suppose that is our U upon L. So that will be equal to energy inside per unit length plus energy between per unit length, and we simply substitute the values, which gets us lambda square 16 pi epsilon naught plus lambda square upon 4 pi epsilon naught natural log of R upon A. And we can just take out the common, and that will be equal to over lambda square upon 4 pi epsilon naught, and it comes as 1/4 plus natural log R upon A. So this is our total energy, total reference energy with per unit length. Okay, so in this case we have to remember that for solid cylinder we always find out the energy which is relative to a reference. Okay, in this reference we have taken it as a, you can say, a hollow cylinder. Okay, if we do not take a reference, our energy becomes infinite, okay, which is not possible. So this was a little bit tricky part here. Okay, I think I forgot to add one question. Okay, 1 second. Yeah, I forgot to add one more question. Okay, the question was quite simple. Okay. We have to find out the energy stored in a sphere of radius r with charge q uniformly distributed throughout the interior. Okay. So let me write out the question itself. The question was, what is the energy in a sphere of radius capital R with charge q uniformly distributed throughout the interior. And once again, we are going to find out what will be electric field inside as well as the outside the cylinder. We can say the electric field outside the sphere and for that a radius r which is greater than the radius of the sphere. And in this case, the electric field is our E, and that will be equal to over Q 4 pi epsilon naught and our R square. And then we have come inside the sphere. For our R which is less than capital R. And for that, we first of all need to find out what will be the volume charge density. So we need volume charge density. And that is our rho, which will be equal to over 4 by 3 pi r cube is the total charge. So this comes at 3 and this is 4 pi and the volume part. Okay. And therefore from Gauss law we can easily write now. So we can say by Gauss law, electric field at a distance r inside the cylinder inside the sphere will be equal to over rho r upon 3 epsilon naught. So we substitute value of rho, and this comes as our q times small r. 3 goes by 3, so this comes as our 4 pi epsilon naught r cube. So we have our electric field inside and outside the cylinder. And let's find out the energy stored. So energy is stored outside the sphere. And outside it means upper limit will be going to our infinity. So we can say our U external will be equal to 1 upon epsilon naught and integral of our r to infinity. And this is our E square, that is our E dV. Okay, so we can just easily write it this as our 4 pi r square times dr. And we already know our electric field, so this comes as 1 upon epsilon naught and integral from r to infinity, and we have over this as q upon 4 pi epsilon naught r square whole square, and we have this as 4 pi r square dr, and this is simple integral, so we can just write the answer directly. It's not much of the complication to solve the integral. So we get our energy at the external of the sphere will be equal to our q square 8 pi epsilon naught upon r. This is energy at the external of the sphere. Now we come to the inside the sphere. Energy stored inside the sphere. And that is our U internal, which will be equal to over 1 by 2 epsilon naught integral from our 0 to capital R. Okay. And we already know the formula, so this comes as a QR upon 4 pi epsilon naught r cube whole square, and this is a 4 pi r square times dr. And we get this as our energy at the internal will be equal to our q square, and this is our 16 and r4. One second, I missed something. Now this looks good. Okay, so we have here r cube will be giving us 6 plus 4, that is 5. Okay, that comes out 40. This is correct then. 40 pi epsilon times r. So this is our energy that will be internal of our sphere. Okay. So total energy that's our U will be equal to U external plus U internal, and we get this as our q square upon 8 pi epsilon times r plus q square 40 pi epsilon times r. Okay, and this gives us 3 by 5 q square 4 pi epsilon naught times r. So this is the total energy that will be associated with the sphere. Okay. Next question. In this case, we are given what is the potential energy of the arrangement of 8 negative charges on the corner of the cube side B with the positive charge in the center of the field as in the figure. Suppose each negative charge is an electron with the charge minus E, while the central particle carries a double positive charge, that is 2E. Basic figure is given to us. So we are given a cube and each corner is having a charge of electron and center one is having a charge of positive 2 times E. Okay. This is comparatively easy. The only thing we have to remember in this case that how many pairs will be of similar charge, how many pairs will be of opposite charge. Okay. that we have only to remember. And for that, first of all, let's identify how many we can say it like as a distance. So if you want to, we know that we have these type of edges for this cube will be our 12. So we are going to have this as our 12 such pairs. And along with this, we can also identify the distance between the opposite charges, and that is our this one, and it will be consisting of 8 such pairs. 4 on the lower surface face rather, or 4 on the top surface, top face. So this will be consisting of total 8 pairs. Then we come between the extreme diagonals, and for that let me draw this something like this. This is the distance between two similar charges, and it will be consisting of only 4 such pairs. So we are going to have this as our 4 pairs. And finally we come to our face and this distance. This distance, and it will be also our 12 such pairs. So this we are going to get as 12 pairs. So in this type of, or specifically with this one, this is the important part. We should be knowing the how many pairs will be of opposite charges and how many pairs will be of similar charges, because energy depends upon them. And because if you look closely, the standard formula for our electrostatic is the product of the two charges divided by the distance upon them. So we already know that our electrostatic potential energy that will be U, and U will be equal to summation, and that will be equal to 1 upon 4 pi epsilon naught first charge, second charge, and distance between the two charges. So this is our standard formula for our electrostatic energy, potential energy. So it means we are only interested between the distance, and obviously charge we know that it is given to us. So that's why we should be knowing how many will be having the same charges and how many will be having the opposite charges. And so the entire cube can be divided into 2 parts. First will be same charges interaction, that is electron-electron interaction, and second will be the opposite charges interaction, that is electron and central charge interaction. So we can say we can split this energy into 2 parts. And the first one will be equal to our electron-electron interaction, which is of our same repulsive basically. And the second one will be our electron, and the central one is given to us as a 2 positive interaction, which is our, so basically this will be a repulsive and this will be our attractive. Okay. So first of all, let's try to find out our first part, that is our electron-electron interaction, or we can say our same charges. So we have our electron-electron interaction. And for electron-electron interaction, you can say we have our edges, there are 12 edges. Okay. Then we have our face diagonal, which are our also 12. Okay. Then we have body diagonal, these are our 4. So total will be 12 plus 12 plus 4. Okay. So we can write this as our, draw a table basically, that is much more easier. So we can say our pair type, and then we are having a distance, and finally we have our number of pairs, because energy is always in number of pairs, in pairs rather, Q1 and Q2. Okay. So we have a pair type, and pair type is our edge, and the edge we know is the distance having a B, and there are 12 pairs. And then we come as a face diagonal. Face diagonal is having a distance of square root of B times B, and total there are 12. And finally we are having body diagonal. Body diagonal is having a distance of square root of 3 times B, and they are total 4. Okay. And so now we can find out the energy contribution per pair. So you can say each pair contributes, and that will be equal to over, because they are same charges, that is E square, and we have 4 pi epsilon naught times R. Okay. Therefore total energy for electron-electron interaction, let us call this as UEE, will be equal to E square upon 4 pi epsilon naught times B, that will be common, and rest comes as a distance part, okay, because B is common to every distance. So this comes as 1 plus, sorry, not 1 but multiply by 12. So this comes as our 12 plus 12 upon square root of 2 plus 4 divided by square root of 3. Now we come to our energy that is associated with our electron and central pair. So we can say that our electron and central pair interaction, and electron and central pair is having only one distance, because that is common. Okay, so we can say our distance, which is our R, will be equal to square root of 3 by 2 times B. Okay. And so we can say energy from one electron, energy for one electron and our central charge, that is equal to our U will be equal to 1 upon 4 pi epsilon naught, and we have one electron and one central atom, and divided by our, let's call this RE. Okay, so we can simply substitute it. So we get our U will be equal to, and this will be equal to our minus, and we have this r is square root of 3 divided by 2, so we are going to get this 4e square and 4 pi epsilon naught square root of 3 times b, and this is for our 1, and they are total 8 electrons. Therefore we can write that for total 8 electrons, we can say this is U center will be equal to, because everything is same, symmetric basically with respect to center, so this simply we can say 8 times our U. Therefore we can say that our U center will be equal to, this is 8 and it will be coming as 32 minus 32 e square 4 pi epsilon naught square root of 3 times b. Now we can simply add them, total energy. You can say our total, let me call this as our U1, much more easier. So we can say total energy, total electrostatic potential energy which is U will be equal to UEE plus U1, sorry, U center. We simply substitute them, and this gets us a U is equal to E square and 4 pi epsilon naught times B, and this comes as a 12 plus 12 upon square root of 3 plus 4 upon square root of 3 plus minus rather minus 32 upon square root of 3. Okay, this will be square root of 2. And we can just combine these two terms, and we get this as a U will be equal to E square 4 pi epsilon naught times B, and this comes as 12 plus 12 upon square root of 2, and this comes as minus 28 square root of 3, and we can write in terms of decimal also. Okay, so we can say U is equal to approximately 4.32 E square 4 pi epsilon naught times B. So this is the total energy, electrostatic potential energy, that will be associated with the tube when the central atom is positive, okay, that is plus 2E, and each corner, each vertex corner one is having a charge of electron. Okay. So this completes for today all the 5 questions. And so today was comparatively questions were easy, except for this last one. Okay, we have to remember the basics of our cube, okay, and identify the pairs. And the second question which we did was with respect to cylinder also. So there we discussed that in case of finding out the cylinder, it's very important to consider a reference point. Find out the energy of a cylinder with respect to reference. If we do not use the reference part, okay, then the energy is infinite. Okay, that was the important conclusion from there also. Okay, rest of things are comparatively easy. So this completes all the 5 questions. Thank you.